Make sure to like and subscribe right now. Yes, do it.
Hello guys, this is Rick from MathEx, and today we're going to be doing the number 21 from the AMC 10B of 2021 Fall Edition, or the number 19 from the AMC 12B of 2021 Fall Edition. Before I go into the problem, I want to make a couple announcements about the channel. First off, me and the rest of the MathEx team are interested in starting a math competition that would probably be known as the MathEx Challenge. We don't have a date or a contest format finalized yet, but we're talking and we're gathering volunteers to help us with this project. So stay tuned for that. Also, me and the MathEx team are investigating ways to make our videos more engaging. We've been doing videos this style, like explaining problems on Microsoft Paint, for a long time now, but it's kind of lame. So we're investigating the Manim software, which is how big YouTubers like 3Blue1Brown make their beautifully animated videos. So hopefully in the future you're gonna see us drop a really cool video like that, like hopefully 3Blue1Brown quality using the Manim Python software. But without further ado, let's just get into this problem. Regular polygons with 5, 6, 7, and 8 sides are inscribed in the same circle. No two of the polygons share a vertex, and no three of their sides intersect at a common point. At how many points inside the circle do two of their sides intersect? Okay, so this seems like a pretty simple but a little weird problem, as you're not typically used to seeing these kinds of problems in geometry or counting. I know for a fact that this is the first time I've seen this problem on the AMC 12 test. But if we approach it with the standard approach and how we attack like new problems, this problem actually goes down relatively quickly. So the first thing you do when the problem introduces you to a process that you don't know is just try it out and get some familiarity with it. So what do they do here? They basically inscribe some polygons in the same circle, and they count the number of ways do the sides of the polygon inside the circle intersect. So I'm going to do that exact same process with the 5 and 6 sided shapes, because those are easy shapes in Microsoft Paint. So I drew my circle, and now I'm going to draw my pentagon and hexagon such that they don't share a vertex and no three sides intersect at a common point. Okay, so here I've drawn a pentagon and a hexagon overlapping, inscribed in the same circle, such that no two of them share a vertex and no three of their sides intersect at a common point. So now we should try to count the number of points that these two regular polygons intersect at. So doing that, we just count. So here I've counted up the number of points that they've intersected at, and we can actually see something pretty neat. The number of points that these two shapes intersect at is 10 points. And this is because each of the sides of the pentagon gets intersected 2 times by the hexagon. You can think of it as the hexagon enters the pentagon and exits the pentagon from each side. So then we can like generalize this to, if we have an A-sided regular polygon and a B-sided regular polygon such that A is greater than B, the number of points that they would intersect on the inside would be 2 times B. And even if we didn't know whether A was greater than B, we could just write 2 times min of A and B. So this is pretty much like the problem, right? And we don't need to worry about any special cases because the problem restricts all special cases. It says they can't share a vertex and they can't intersect at a common point. So all interactions happen like this. So if we want to think about the number of times the pentagons, hexagons, and heptagons get intersected, we just need to keep in mind this like formula. So I'm not going to draw a heptagon and an octagon on top of this already existing pentagon and hexagon because it'll just muddle up the image. But we can think about the number of sides that each of these shapes will get intersected at. So if we just think about the hexagon, right? The hexagon has less sides than the hexagon, the heptagon, and the octagon. So each of its 5 sides will have 2 entries, will have an entry and an exit point from each of the 3 larger shapes. Similarly, with the hexagon will have an entry and exit point from each of the 2 larger shapes, the heptagon and the octagon. So we'll get 6 times 2 times 2. And finally, the heptagon, right? On all 7 sides of the heptagon, we're going to have an exit and entry point from the one larger shape, the octagon. And since the octagon is the largest shape in the diagram, there are going to be no such entry and exit points. So this expression will give us the number of points that the polygons will intersect inside the circle. So computing this expression out, we get 30 plus 24 plus 14, or 68, which is our final answer. So as you can see, even though this problem is an entirely new concept, we can just solve it by going about the general problem-solving strategy, just testing out the conditions of problems and trying to find a pattern. And doing that, we can actually solve this number 21 in under 2 to 3 minutes. Just a completely novel problem, just destroyed just like that. So I hope you keep this strategy in mind and apply it on future problems you get stuck on. I know this strategy has helped me a bunch on AIME. So this is a pretty useful thing to practice and be able to do. But other than that, thank you for watching the video and watching the problem. And stay tuned for the introduction stuff I mentioned earlier, right? Stay tuned for our hopeful Manim videos. I'm hoping to cover conic sections using the nice software. And stay tuned for the MathEx challenge, which I'm going to release more details later.